the idea, right, of controlling the experiment and randomizing the treatments is really a key idea in causal inference. Why? Because let's say we give the treatment and one of the groups, we didn't randomize it, and the doctor gives the treatment to the people he thinks that will benefit from the treatment, right? So he doesn't randomly choose. He actually decides that based on his judgment, he's going to give the treatment to those that should benefit from it most. Well, then if we take that group, it's going to be biased. The treatment effect is going to be biased because we're going to have selected people that we think would benefit from the treatment to be treated. So the idea is that if we don't do a controlled randomized experiment and we just look at how things are happening in the world, right? So we call this real world evidence or observational data. It has different names, but we kind of have to, we can't just look at, okay, who received the treatment, who didn't receive the treatment, and compare them. Because this comparison will be biased for a bunch of different reasons, like the one I just gave, where, well, doctors give treatments to people that should benefit from them. They don't just randomly give out treatments. Or we can think of other settings where we look at, I don't know, people that choose one university versus another. Well, maybe the people that choose the university want to go there because they think it'll be better for them. And the ones that went to the other one, they just didn't get accepted in the other university. And now we're making a biased comparison. We can't say that this is the university that necessarily makes things better and things like that. So when we're looking at the real world, there's a bunch of these sort of confounding patterns in the data. We can't just compare groups as if they were similar. We have to make sure that we can make meaningful comparisons. So we have a bunch of techniques to do this. One of the main tools that statisticians use is propensity score modeling. And this is important for different reasons. It's really important in the theory behind why this works, but it's also important because it's a convenient tool to eliminate confounding from observed variables. So take the example that Darko said, where we record a huge biomedical database from a hospital or something. Some scientists or some researchers are thinking, hey, this is really interesting data. Maybe I should pull all that data and try to answer some questions that are interesting. If the researcher doesn't think about the different possible confoundings, right? So I don't know, people in this group are a lot older, or people in this group are not representative of what we would expect in another situation or things like that. The associations we're going to measure are going to be biased. So when we have a lot of variables like this, and this is a kind of study I've worked on before, we can use all the variables that we think are confounders or that we have good reason to believe that are confounders, and use what we call a propensity score model to try to eliminate that confounding. So in the example I'm talking about, we had, it was observational data just from a database. We did a lot of cleaning. We had like a population of about, or a sample, we could say, of about 1,000 patients. And there was two things we were trying to compare, but we know that this comparison is biased by, I don't know, 30 other variables that we measured. So we take these 30 variables, we put them in a magic tool called the propensity score model, and then we can use these propensity scores, which are a sort of model of how people are given the treatment or the control. We can use this tool to eliminate confounding. Now, we're always limited by the problem that we don't measure everything. We don't observe all the variables in the world. So then we can even go further and do other types of analyses to make sure, okay, there's still some confounding that comes from variables I didn't measure, but maybe I can prove that it's so small that my conclusion is still valid, right? And